Hi guys, my name is Briell King, and today we are going to be talking a little bit about electromagnetic radiation and electromagnetic waves in general. So one important thing to note that makes electromagnetic waves different from other kinds of waves is that they actually don't require a material medium to pass through. So for example, like sound waves, you have to have air or something there in order for them to transport effectively, but electromagnetic waves can actually travel through a vacuum in space, which makes them unique from other kinds of waves. Most people tend to forget how often we actually use electromagnetic waves. So, X-rays and microwaves are a couple of the most obvious ways that we utilize them, but also in long-distance communication, so cell towers and radio towers also use them. Our most important source, though, is the sun. Scientists knew for a long time that if you ran a current through an electric wire going one way, then you would in turn, like I'm drawing, have a magnetic field induced going around that wire. So they were wondering though, could you theoretically create an infinite magnetic current induced by an infinite electric current? It was through these studies that they actually ended up discovering electromagnetic radiation, and they were able to figure out how to bring it about. Instead of having an electric field that ran one way, in turn creating a magnetic field that ran one way, they found out that if you could have an electric field that varied over time, then you could also have a magnetic field that varied over time. A really influential scientist in this field of thought was named James Clerk Maxwell. He had a pretty sweet beard and some interesting hair, so we'll draw that. But what he did is he combined his thinking with 4 different ideas and equations of different scientists in order to come up with a new set of equations to explain electromagnetic waves as we view them today. The first rule is known as Gauss's law of electricity. By the way, I'm not going to write out any of the equations for any of these rules because they're really long and complicated and you only need to understand the main ideas behind them. But the main idea behind this one is that electric field lines originate on positive charges and terminate on negative charges. The second rule is known as Gauss's law of magnetism. The main idea behind this one is that magnetic field lines, they actually don't really have a start or an end. They are infinite. The third rule is known as Faraday's law of induction. The main idea behind this one is that a changing magnetic field can in turn induce what's known as an EMF. We sometimes refer to these as electromotive forces. And finally, we have the fourth rule, which is known as Ampere's law. This is basically the third rule we talked about, just switched around. So it says that a changing electric field can in turn induce a changing magnetic field. So before we move on, I'm going to talk about a couple of constants that are introduced in the first and second law. From the first law, we learn that the strength of the electric field is proportional to a constant known as the permittivity of free space. For the second law, we learn that the strength of the magnetic field is proportional to a constant known as the permeability of free space. I'll give you the values of these later on. Maxwell used this equation and plugged in the 2 constants in order to figure out what speed electromagnetic waves moved at. By discovering that it was the speed of light, he was able to make a really big discovery that light itself is an electromagnetic wave. Alright, I'm going to slow down this video because this is probably the most important part of the whole video. Now we're going to talk about how Maxwell's equations and the discoveries of other scientists all worked together in order to form this model of electromagnetic waves. On the left, I drew what's depicting one test charge, but it's just switching its electric field back and forth rapidly. On the right, I drew the graph for what is going to be our 3D depiction of an electromagnetic wave as we view them today. First, we'll draw our electric field on the y-axis. So if we're acting off of the electric field depicted in the leftmost test charge, you'll see that it pulls the electric field up. But then, as the test charge switches to having the opposite electric field, it pulls the electric field back down. So we get this nice propagating curve that's going at a super fast rate. Now we will draw the magnetic field, which is on the z-axis. So you'll see if we use our right-hand rule, on the leftmost test charge, the magnetic field is going one direction. But then if we use our right-hand rule again, we will see that the magnetic field then changes. So as the electric field on this test charge changes, so does the magnetic field. We can draw this by, again, showing a propagating wave that is propagating at the same rate as the electric field, just perpendicular to it. An important thing to note is that on the x-axis, this is the velocity of the wave, which, as we proved in the last slide, is actually just equivalent to c, or the speed of light. I just wanted to give the values of the constants we've used really quick. So speed of light is equal to 2.99 times 10 to the 8th meters per second. Permeability of free space is equal to 4 pi times 10 to the negative 7th Tesla meters over area. Permittivity of free space is equal to 8.85 times 10 to the negative 12th Faradays per meter. The first equation that's really helpful when dealing with electromagnetic waves is this: electric field equals magnetic field times speed of light. This holds true in literally every situation. Another equation is what can be used to solve for the average intensity, or basically like the energy that an electromagnetic wave holds. It can be written in one of these three different ways, just depending on what you're given. So if you're either given the electric field or the magnetic field, you can then use any one of these three equations to solve for your average intensity. Then your max intensity can be found just by multiplying your average intensity times 2. I'm not going to do any example problems with these because it's literally as simple as just plugging in your values. So just to clarify really quick, your electric field is in terms of volts per meter, your magnetic field is in terms of Teslas, and your intensity is in terms of power over area, which usually equates to watts over meters squared. Before we talk about the electromagnetic spectrum, I just want to clarify a couple things really quick. So this is what we will refer to as one wavelength or one lambda. These are in terms of meters when we plug them into equations. However, they're normally given to us in terms of nanometers because a lot of times they're really small. So now I'm going to talk a little bit about frequency, which is in terms of hertz. I'm going to draw two different kinds of graphs, and they will both be equivalent to 1 second in time. On the left, we are going to draw one wavelength. So in this one, there was one wavelength that propagated in 1 second, which, as you will see, is a lower frequency than what will be on the right. On the right, I'm going to draw one wavelength and then add a second one. So in the same amount of time on this graph, we were able to propagate two wavelengths instead of just one, which is a higher frequency. This is because in the graph on the left, this one had a longer wavelength than the one on the right. Thus, we can see that frequency is inversely proportional to wavelength. Now we are going to talk about the electromagnetic spectrum. So this basically just refers to all of the electromagnetic waves that we know of at this point in time. On the next video, I am going to draw kind of a graph of how they each relate to each other in terms of increasing frequency. Some people like to do it by increasing wavelength, but increasing frequency is just the method that I prefer. First, we have radio waves, which vary from about 1 meter to 10 to the negative first meters. Next, we have microwaves, which vary from 10 to the negative first to 10 to the negative third meters. Next, we have infrared waves, which vary from 10 to the negative third to about 10 to the negative sixth meters. And then in between infrared and ultraviolet, we have the visible spectrum, but I'll talk about that later. Ultraviolet light varies from about 10 to the negative 7th to 10 to the negative 8th meters. X-rays vary from about 10 to the negative 8th to 10 to the negative 11th meters, and then gamma rays vary from about 10 to the negative 11th to 10 to the negative 13th meters. Since the visible portion of the electromagnetic spectrum takes up such a small portion of it, I just wanted to draw a little bit zoomed in. So in between infrared and ultraviolet light is what we refer to as the visible spectrum, and this just includes all of the colors of the rainbow. This spectrum varies from about 700 nanometers to roughly 400 nanometers, and it just includes all of the colors we can see in everyday life. Okay, now we are going to learn about a couple equations having to do with electromagnetic radiation. So first up, we're going to learn c, or the speed of light, equals lambda times frequency. The second equation we're going to learn is E, or energy, is equal to h, which is Planck's constant, times the frequency. So there's different professors that use different values for c and for h, but we are going to define c, the speed of light, as being 2.99 times 10 to the 8th meters per second. And then Planck's constant, we're going to define as being 6.626 times 10 to the negative 34th joule seconds. Okay, now let's do an example problem. I know that there's a few more equations relating to the electromagnetic spectrum. However, I'm not worrying about those because there's a group that was assigned that entire topic, so I'm just barely covering it since it kind of relates to electromagnetic waves. So your first step is to take your wavelength that you're given, and if it's given to you in something other than meters, make sure you convert it to meters. So that's why I'm converting nanometers to meters right now. The equation that we will be using for this problem is C equals lambda times frequency. Then all we have to do is rearrange the equation so that we're solving for frequency instead of speed of light. After that, all we have to do is plug in our values since we have everything that we need. Just keep in mind that we didn't talk about a lot of other things. For example, how to find the period of an oscillating wave, or how to find energy if you're only given wavelength, for example. Just know that there's some other videos that cover that, so if you're wondering a little bit more about that material, make sure you go check out some of the other videos that people made. Overall, electromagnetic waves are a really influential part of our lives, and I think we tend to forget about how important they really are. Thank you for watching. Stick around and watch the next couple of slides to view my sources.